75% of New York City crosswalk buttons are fake. They don't actually do anything. You might as well not even press them. You may have heard this before. You might even believe it yourself. And honestly, it sounds plausible. How many times have you stood in an empty intersection, pressed the button, and waited anyway? Or watched the person across the street go, even though they got there way after you? And if that's true, it raises a much more interesting question. Why install thousands of buttons that don't do anything? Why pay to maintain them? And why keep replacing them when they break? To figure out if cities are actively lying to you, we have to look at the invisible system making the decisions. And to do that, we have to start at the bottom, the dumbest traffic light in the world, a blind timer. And once you see that, you'll never look at a traffic light the same way again. Let's start with the dumbest version of a traffic light possible. No cameras, no sensors, no AI, just a clock. This is called a fixed time signal. It is exactly what it sounds like, a timer that runs the exact same pattern all day, every day, whether there's one car at the intersection in the middle of the night or 100 cars waiting in rush hour. When designing a fixed time signal system, engineers look at two main numbers. The first is the cycle length, the total time a complete cycle takes start to finish through every phase. The second number is the split, how the cycle gets divided up between directions. If north-south traffic is heavier than east-west, north-south gets a bigger chunk of the cycle length, say 55 seconds of a 90-second cycle, while the cross street only gets 35. That's it. That's the entire system. You might be thinking, okay, but how often is this used anymore? And surprisingly, it's used more often than you think, especially in places like downtown areas where traffic is predictable enough that a timer works well enough. If roughly the same number of cars show up every weekday at 8 a.m., why build something more complex? But the second that traffic stops being predictable, the second you get a quiet side street that floods randomly when a concert is in town, or a left turn lane that sits empty 90% of the day, this approach starts wasting everyone's time. We all know the feeling, sitting at a red light for nobody. So this begs the next question. What if the light could tell when a car was waiting and change accordingly? And that's where things start to get interesting. So the engineers gave the traffic lights eyes, or something pretty close to it. If you look down at the pavement near most intersections, you'll probably see it. A faint rectangular cut in the asphalt, sometimes shaped like a diamond. That is an induction loop, a coil of wire buried just under the road surface. Here's the part most people get wrong. It isn't a pressure sensor. It's not weighing your car. The loop has a small electric current running through it, generating a magnetic field. When a big chunk of metal, like, a car, sits on top of it, that metal disrupts the field. The loop detects the change and reports back to the traffic light that something is there. This is also why it's called an actuated signal. The light is no longer running blind. It knows, to an extent, what's going on at the intersection. It's responding based on actual input. If there isn't a car waiting on the side street, it'll simply skip that phase and keep the main road green. Car shows up, trigger the cycle. This also explains a phenomenon you've probably seen before without knowing exactly why. Motorcycles sitting at a red light that never seems to change. A motorcycle is mostly metal, sure, but it's just a fraction of the mass of a car or a truck. Oftentimes not enough to meaningfully disrupt the field. The detector just doesn't see it. But these systems still have one major limitation, and it matters for where this story is going. Each of these decisions is local. The intersection only knows about itself. It has no clue what's happening 1 block away, 2 blocks away, or even across the city. It only changes based on the current situation right in front of it. That's a perfectly fine way to think about just one intersection, but a city is a network of hundreds of intersections, all touching each other and feeding traffic into one another. So what happens when each intersection makes the smart local choice, but those choices conflict with what's happening down the road? That's where this story stops being about single intersections and starts being about the system. Here's a little thought experiment. Imagine every intersection on a street is smart in the way we just described, each one reacting perfectly to its own local traffic. Sounds great, right? Except now imagine you're driving down that street, you hit a green light, then half a block later, you hit a red one. Then green again the next one, but then red again the next one after that. Every single intersection made the locally optimal choice, and the result for you is one of the most annoying driving experiences possible. Stop, start, the whole way down, all the way home. This is the classic trap of local optimization. Every individual decision can be correct, and the system as a whole can still be terrible. So traffic engineers made a deliberate trade-off. Instead of letting every intersection optimize purely for itself, they introduced a third variable, alongside cycle length and split, called offset. Offset is just a timing delay between intersections. If you know it takes roughly 15 seconds to drive from one signal to the next at the speed limit, you can deliberately turn the next light green 15 seconds after the one before it, and the one after that 15 seconds after that. String enough of these offsets together, and you can get something engineers actually call a green wave. A rolling wave of green lights that moves down the corridor at exactly the speed traffic is supposed to travel. Hit the wave right, and you can drive a mile through a dozen intersections without ever touching your brakes. But notice what had to happen to make that work. Some intersections are no longer making the locally best choice. A side street might get a worse split than its own traffic would justify, purely so the main corridor flows better. One intersection's efficiency gets sacrificed for the system's efficiency. This is local versus global optimization, and it shows up everywhere outside of traffic too. Network routing, resource scheduling, even hiring decisions in a company. Optimizing every individual unit in isolation does not automatically optimize the whole. Sometimes the whole only works if individual parts accept being slightly worse off. And once a city is looking at this level, there's an obvious next step. What if the system didn't just follow a pre-planned wave? What if it could watch traffic in real time and adjust the whole thing on the fly? So far, everything we've talked about is still, in a sense, pre-planned. Fixed time signals run on a fixed schedule, actuated signals react, but only locally. Even the green wave, as elegant as it is built on a prediction. Engineers calculated the offset in advance, assuming traffic would behave a certain way. But real traffic doesn't read the plan. A concert lets out, a lane closes for construction, it's Black Friday. The moment actual traffic deviates from the assumption, the whole carefully tuned green wave starts to fall apart. So the next evolution was to stop pre-planning entirely and build a system that watches traffic happening right now and rewrites its own timing on the fly. These are called adaptive signal control systems. Here's the core idea. Instead of just one induction loop per lane sitting right at the stop sign, these systems place sensors upstream, further back from the intersection. That gives the system a few seconds of advance warning. Traffic is building up, here's how fast, and here's how much. The data feeds into a central model that's constantly asking, given what's happening on this corridor right now, what's the optimal cycle length, split, and offset, recalculated continuously, every few minutes, sometimes every cycle. This is the shift from a static program to something closer to a live control system, the kind of feedback loop you'd find in something like a thermostat or a cruise control, just operating across an entire street network instead of one device. Sense the current state, compare it to the target, adjust, repeat. And the results are real, not theoretical. Deployments have been measured reducing traffic delay by something like 25% compared to fixed coordination, just from replacing a fixed plan with a constantly updating one. So now we've got the full picture, a timer that became reactive, that became coordinated, that became adaptive. 4 layers, each one solving the failure of the one before it, which brings us back to a button you've pressed 100 times, and a claim you've probably heard that we still haven't actually answered. So let's go back to the claim, 75% of crosswalk buttons in New York do nothing. Here's the thing, that statistic is basically true. The city itself has confirmed the vast majority of pedestrian buttons in NYC are non-functional, left over from an older signal system. So why are we calling the original claim misleading? Because does nothing and is fake are not the same thing. Think back to everything we just walked through. A modern signal isn't a light switch that one button can flip. It's a scheduling system, juggling cycle length, split, offset, and, at the adaptive layer, live sensor data, all balanced across an entire corridor. A button that instantly turned a light green the moment you pressed it would break the entire system. It would let one pedestrian override a calculation built for hundreds of cars and pedestrians across the whole street network. So instead, that button does something much less dramatic, but far more honest. It submits a request. It tells the system a pedestrian is here and would like a walk phase. The system decides where that request fits into everything else it's already balancing. Sometimes that means the walk signal comes almost immediately, because the system was already about to give that phase anyway. Sometimes it means waiting, because your request just got slotted in behind decisions that were already in motion. That's also why pressing it after the light's already counting down does nothing. You're not flipping a switch, you're submitting a request to a phase that's already started. This is the framing ped safety used that fits perfectly. It's not a light switch, it's a reservation system. You're not turning anything on or off, you're getting in line. So the button isn't fake, it's just honest about something most of us never think about. You're not the only priority in the system. You're one input among many into a piece of infrastructure that's been quietly running a real-time optimization problem this entire time. So here's where we end up. The button you've been mashing impatiently for the last 20 years isn't broken. And it isn't fake either. It's an input into a real-time distributed scheduling system, one that's been quietly running underneath every city you've ever walked through. And once you see it that way, you start noticing the same pattern everywhere. A timer that became reactive, a reactive system that learned to coordinate, coordinated system that learned to adapt in real time. Local decisions balanced against global ones. Every layer solving exactly the problem the layer before it couldn't. That's not really a story about traffic lights. It's a story about how you build any large system that has to serve thousands of competing requests at once, whether that's cars on a street, packets on a network, or tasks on a server. So next time you're standing at a crosswalk, pressing a button that doesn't seem to do anything, you're not pressing a switch, you're submitting a request. And somewhere, a system that's been optimizing traffic since before you were born is deciding where you fit in. If this changed the way you think about something you walk past every single day, that's kind of the whole point of this channel, finding the invisible systems hiding inside ordinary things. So if you want more of that, subscribe. And if you know someone who spent years angrily mashing a crosswalk button, send them this video. They've earned it.
Wait.